So this is lecture 23 on invariant maximality derivations by Harvey Friedman, please.
Thank you. Um, okay, so today it took me a long time to sort out what I could and could not do with interval extension usabilities. It's now stabilized pretty well. Um, it's the last lecture I want to give on this. I want to move on to finite choice, invariant finite choice, and explicitly pi zero one sentences. uh, and get into that. We've spent a lot of time on this chapter three, I have to do some more work on chapter three, not major work, but some exposition on. You'll see some exposition of what I can't do and how maybe it can be done with more research, because there's a lot of open questions here. Uh, okay, so the book, the six chapters have not been changed for a long time, and yeah, so this is starting. I'm starting to understand how to write the introduction. Haven't done it. This we talked about a long time ago. Needs some polishing. This is what we've been talking about recently a lot. This is right now engraved in stone and not uh, revisited. Spent a lot of time on that. So next time I want to start talking about this. Uh, okay, so and then this chapter hasn't, the table of contents hasn't changed until we get to the uh, very end. So this is finite usability, and that was completely successful. We figured out all the usabilities in the gave a characterization, not very complicated, uh, uh, called fin use. Yeah, actually, there are two forms of fin use now, but they're closely related. And this whole thing is done in RCA naught. So now the issue, okay, and then if you remember, we took these particular special functions, which are the simplest ones that are infinite, and we worked out with some care about what systems how much machinery we were needing. For example, here we used Erdős-Radó to argue that we just needed that cardinal. So I was careful to do that. Um, and so this is very stable. This hasn't been revisited. Um, and fully K usable is the same as fully two usable all through here, it turns out, that we do have that. All right, so then I did some formal work on that stuff that I just described. Some formal work about the exact formulation of the systems in which things are proved, instead of just using informal statements like using a cardinal. So we actually get a little more explicit about stuff here. Uh, all right. So we've been talking about this, and this has gone under a lot of changes, and I have to retract stuff, take stuff back, put stuff back in, whatever. I think it's stabilized here now. So we're going to talk about this. Let's see. I think we already talked about indiscernibles. I like to use indiscernibles. I didn't do that over here. I over here when I argued over here for the usabilities back here. When I argued, sorry, seven. When I argued for the usabilities, in the middle of the argument, I applied Ramsey theorems of various kinds, including ones that don't do RNZFC. Um, I uh, yeah, so I applied the Ramsey theorems in the middle of the arguments. These arguments there's something more complicated about the structure. Well, there's something more complicated about what I do in here because I wanted to be careful about how big K is. Um, and yeah, yeah, K and N, how they affect things. But besides that, the putting that aside, the stuff we're doing today in this section 3.9 is more intricate in some sense than this, and that's more intricate in terms of being careful about how much you use, how much cardinals you use. So um, yeah, so what I did back in the 3.7 was that the Ramsey arguments were integral part while I was doing the proof, so to speak. Whereas here it's because it's more intricate in certain ways, it's I think it's clearer and nicer to first do the Ramsey theory in advance of the arguments that to which it applies. In other words, don't integrate it. And so I separated out, and I think we already talked about this. So I have indiscernibles. Uh, and these are indiscernibles that you can only get with large cardinals. So I use these intervals. I don't get into the issue of what can you do in smaller systems in here. There's a lot of further research that's pretty obvious that's needed, uh, beyond the book. Like, I don't want to try to do everything. So uh, so today well, we've done this in many different forms, but I'm just gonna go through it again. Uh, uh, oh, you have a finite function f, and you extend it. So this is interval extension usability. You have a finite function f, and you extend it by the identity map on this interval, and it's from -1, 0. And here I do it when it's in the middle, minus a half, a half. This creates some more complexities. And I do it in case this is contained, the functions live in there. And I also have the identity function on the endpoints. There's a reason for this. It looks a little technical, but this is a good idea. The reason it's a good idea is I use both 2 and 3 to prove this, that if -1 and 1 are not affected. Now, that's a notion that was introduced a long time ago in this chapter. -1, 1 not affected. It means that uh, it's not there. A number is not affected if it isn't in the field. The only way a number gets affected is if you move it or the inverse moves it. You either move it or it's a value. You either move it or it's a value. By move it, I mean you can't make it, it's not the identity, it's a number. Okay. There's several ways to say that. Another way to say it is you're not affected if you're outside the field or you're moved. Well, yeah, that's right. Or you're moved. Yeah. Okay. I probably should add in the final version several different ways to say not affected, but it's basically what you think it means. So in order to do this, I need these two things to get this. Um, because if it's not affected, you can assume up to isomorphism. It kind of looks like this. This is what. All right. Then there's another case that I can do. So these are sufficient. These are all sufficient. This is sufficient. Um, this and this are sufficient. Um, this this could this 393 follows from 394. 394 is stronger. So these are two sufficient conditions, 392, 394. And there's another totally different kind of sufficient condition called radial, which came up, by the way, in the finite theory. There's another sufficient condition called radial. And in 396, I try to consolidate all what I know about what's sufficient. And we're just talking about one interval extensions. We're only talking about a finite function extended by the identity on an interval. That's all we're talking about. And already this seems to be very difficult, very tricky. Um, so uh, I consolidate a lot of information about the sufficiency. Now, necessity, I know very little about necessity. I have been bad at figuring out elementary proofs of refutation that certain functions don't work. By the way, strictly increasing is long, long ago, we proved that strictly increasing is required for full usability or even two usability. So strictly increasing is not negotiable. Everything else is, except that we are talking about just extending a finite function by the identity function on an interval. And I thought that I could characterize this completely, although, but the problem is that I haven't been good at finding elementary arguments to prove things are necessary. So there is a plan of how I might show necessity with a lot of work by going back into the reversal, deep down into the reversal, and making the reversal reverse 1 = 0 and not just con SRP. So this is kind of an exciting thing, but I don't want to try to do this while I'm writing this book. It's not it's not going to be in the book. It'll just some comments about strategic ways of trying to do this. And of course, if you're going to add more than one interval, and you go to the more general thing called almost identities, there's the level of ignorance I have is exponential, is iterated exponential, is far more. So this is quite an interesting development that this is so much wide open. It seems to be so much wide open. All right. Um, I would guess I won't have much time to talk about much of this, but I will talk about joint usability briefly. This is important, and for very interesting reasons. It's more important than you might think. Joint usability. All right, so let's see what we've got here. Last lecture on chapter 3. Next time we talk about uh, explicitly. Yeah, because everything's implicitly positive 1 in this whole book. Yeah. All right. So this is something we've done a lot in different forms. Let's just review it. So um, I have a convention. I guess I didn't say it here uh, in this section 3.9. F always denotes a finite function, and J always denotes a rational interval, which has to be non which has to be uh, rational endpoints, non-degenerate. Yeah, I have this old notion way back. I fixed this, set it up so that there's a thing called a general rational interval. A general rational interval could be degenerate or even empty, but a rational interval is only allowed to be non-degenerate, and always the endpoints have to be rational, and the elements are rationals. Yeah. Whoops. Here we are. Oh, and U dot. Might as well say this. U dot is disjoint union. Okay. All right. So first of all, a normalization. If I have anything like this, F union, now remember F is finite, F union dot identity on -1, 0, uh, that's strictly increasing, then I can make sure that I can still keep it strictly increasing and have 0 and 1 in the field of F. 0 and 1 in the field of F. It's just convenient. It's not really totally necessary to make this move, but it's convenient when you actually prove that that these are usable. It's nice to have some some particular stuff around. You don't have to worry about degenerate cases that there's nothing there and stuff like that. And this is trivial actually, uh, that you can always do that. So so we're going to fix a strictly increasing G whose field includes 0 and 1, and the field and the cardinality of the field will be n of F will be n. And we show that G is fully K usable. And we fix an order invariant C. Just a second here. I'm going to format this when I see little mistakes in the formatting. All right, here we go. Yeah. Yeah, I didn't have a chance to format it as well as I normally do. Like that should be a union sign. It should be a cross product. Uh, here we are. Okay, so there's a pattern in which I do these things because today we're going to do three of these things. We're going to go through three of them. First I define a space, and that's transfinite, got transfinite stuff in it. And this one is a union. It's the Cartesian product of okay. So the indiscernibles, I should say, maybe out front here. Yeah. Also, we use strong indiscernibles. I equals uh, lambda 1, lambda 2. Just omega them. We just of type omega. Um, yeah. So not to confuse this one, I like to put the Greek letter in. Here we are. Yeah. Yeah. So we have indiscernibles. The set of indiscernibles is I, and lambda 1, lambda 2, lambda 3 in order. Here we go. Okay. Okay, so we fix this. Okay, we make up a space. We make up a space strategically. Lambda n cross this rational interval, union this single point at the top. And we make the obvious linear ordering, well, not so maybe not so obvious. Where this comes first, this comes last, of course. Um, and on here, it's just a lexicographic order with standard less than on here. Lambda of n is an ordinal, right? It's the nth indiscernible. And standard less than on 0, 1. Less than q is an effective linear ordering of q of type omega. With left endpoint 0. Yeah. Okay. Now, the way these things are done, that there's always a tension between the obvious left-right, between the left-right and a carefully chosen well ordering, and a carefully chosen well ordering. And the well ordering is used, the left-right is to try to imitate the rationals. Remember, we're going to bring this back down to the rationals. This is transfinite right now. And the ordinals, the well ordering is used to do the greedy construction, to do the transfinite recursion. That's how this is always done. All right. So in this well ordering, as you'd expect, this comes first and this comes last, just as before. But the difference is that on here, this is the lexicographic ordering with standard less than, but with less q on 0, 1. So in this particular case, the contrast is very simple between the dense linear ordering and the well ordering. Namely, the well ordering is just the same as the dense linear ordering, except the second coordinates are well ordered by less q instead of just being the dense linear ordering on that interval, right? Okay, and then of course I just extended lexicographically. I extended to k-tuples via what's called maxlex, as you know, as like here. You first look at the biggest one, and then if that's smaller, you're done. And then if they're the same, then you do order lexicographically. Yeah. Okay, just to make sure that everybody's on the same page, we describe some facts about these orderings. Less than star is dense with left endpoint 0, 0, right endpoint lambda n 0. Less than double star is a well ordering with left endpoint 0, 0, right end, same thing, but it's a well ordering. And in less than double star, the k-tuple version, the left endpoint is this k-tuple, and the right endpoint is this k-tuple. Okay, now we want to extend. Remember, we were given an order invariant E in the outset, right? This is our constraint. We're trying to prove usability. This is our constraint. And we extended transfinitely by taking the set of things which are order equivalent to an old thing. But this is with respect to this one. We certainly don't want to use the other one. Okay. In other words, it's a set of it's a set of KR tuples which are order equivalent to one in the place where E lives, which is minus 1, 1 rationals. Okay. And instead of talking about order equivalents in two different orderings, I just bring it down to isomorphism, which is a nice way to say the same thing. Now we make the transfinite greedy construction. So X is in the set if and only if, when you restrict it to how far, to up to that point, and you try to tack on X, you still have you still maintain the constraint. The constraint is having all R tuples in here. That's the constraint, right? Okay, so this SE kappa KR is maximal among the subsets of WK, all of whose R tuples lie in EKR. Now, this is obvious because maximality is a weak special case of greed. Greedy is a very strong form of maximality. Okay. Now, this magic set, which is this greedy set, is actually very definable. It's the set of all elements of our space satisfying a first order condition um, over V kappa. First order condition over V kappa without parameters. All right, now the next lemma uh, is an immediate consequence of the indiscernibles. The indiscernibles. I'm saying if you have x and y that are in this Cartesian product or among the indiscernibles that we use to build W, our space. See, we're not looking at all of W here. We're just looking at, see, we're not looking at all of W. W will have all kinds of things like all the things in lambda of 2 cross 0, 1, for example. Assuming n is greater or equal to 3, that's a immediate part of W. So we're just talking about this part together with all these extra ones here. Uh, so suppose they're order equivalent, and suppose they agree on this core here. Okay. Um, In other words, the way I say agree, there's a nice way to say it. Xi is in this core, or Yi is in this core implies Xi equals Yi. So if one of them is in the core, the other one has to be the same thing, and not only in the core, but the same thing. Then X and Y are membership is the same. So this is a kind of indiscernibility for the context we're in. Indiscernibility with parameters from here. Uh, And that follows from the fact that we've already gotten our indiscernibles beforehand, by uh, general, general transfinite combinatorics. And then you use this to prove that G is fully usable. I guess I decided not to get into the details of these proofs, um, but they're fully done in the manuscript that you don't see yet. All right, but Uh, so the idea is that I have a kind of maximality and indiscernibility already, and I start with a structure that has all these elements in it. The domain of the structure is capital W, my space, and it has this set here as a k-area relation in the structure, and then it has all these constants for these indiscernibles. And it has less than star as a binary relation in the structure. That's important. And then you take a countable elementary substructure. And when you take a countable elementary substructure, uh, that's going to be of order type the rationals from -1, 1 closed, and the indiscernibles. You take a countable elementary substructure, but then you take an isomorphism into the rationals after you take the countable elementary substructure, and you get the indiscernibles are mapped to the elements of the field of F, Remember, f is a finite function in the rationals. And and this interval becomes the interval from by the way, this is screwed up here. Yeah, no, this is right. This interval becomes the interval minus one comma zero when we make the isomorphism. Yeah. All right. So this just summarizes what we proved. Every strictly increasing G equals F union the identity from minus one, zero, uh, F finite is fully usable. Yeah, okay. Now that proof used those indiscernibles, which in turn uses SRP plus. You can get away with RCA naught. Uh, no, I'm sorry. You can get away with WKL naught plus con SRP. You can get away with that by various machinations of the kind that we have done in the past. You work with non-standard models you're fearless. You don't care if you have large cardinals or indiscernibles inside your non-omega model. You just bear with it, and then everything comes out nice. All right. This one is harder, kind of more interesting. So suppose that core identity part is in the middle, and the whole thing stays away from minus one, one, because it's inside minus two-thirds, two-thirds. Except that I am going to allow that it's trivial on the endpoints. That okay? Then I can actually then I know it's fully usable. And let's talk about a little bit of how this works. So I let G be like this. Uh, then G, I can extend G so that and this is always useful to have this, so that the field includes minus two-thirds, one half, and two-thirds. And this is easy to do, that you can do that. Keep it strictly increasing. The basic idea is if two-thirds is not affected, then you can map minus two-thirds to itself. And if same thing with all these things, that you can always make it the identity if it isn't really being used at all. You see, you can do that. All right. So now we've fixed one of these gadgets. Uh, uh, field. Oh, I, in order I don't want to make up new letters, so I just recycle the old letters and warn you in advance that I'm recycling the old letters and changing their meaning to to adapt it to this particular uh, section. Okay, so I fixed this one. Actually, I repeated myself, didn't I? Whose field includes this? Yeah. Yeah, I should probably put this over here and erase the second copy, but we don't care about it. We're talking uh, about this. I'll fix that up. Okay, we furthermore assume that the cardinality inside here is n, and the cardinality outside here is n. The lower part has cardinality m, and the higher part has cardinality n. Fix an order invariant e's. So now we do our space. We develop our space and argue as before, uh, but it's trickier. So you gotta be more careful. Yeah. Okay. So what does this space look like? Well, it's a mixture of rationals. It was always before a mixture of rationals and ordinals, right? Okay, so the first thing is -1. Uh, and the second thing we have from left to right is this left closed, right open ordinal interval, the endpoints being indiscernibles, ordinal interval, uh, cross 0, 1. This is to make things dense. Together with also this stuff, lambda of n plus 1, m plus 1, 0, this one point, and then a Cartesian product, lower down, by the way, union this single point together with this single point, right? And the way this is constructed, this has to do with the direction in which the transfinite recursion is conducted. The transfinite recursion um, will be seen, well, that's down here, but let's down here. It's going to be explained down here, but let me say something about it. The transfinite recursion starts here. The transfinite recursion starts here because this is the one that has 0, comma, uh, little bugs in here. This is the one that starts with 0, comma, 0, you see. The transfinite recursion starts here and goes all the way to the end with 1. Yeah, I mean, it goes all the way to here and then pauses and jumps to 1 and then starts to come back all the way down here and goes through up here. I know this is weird. Up through here. This is the last of it. Yeah. See, there's a delicate interaction between left, right, and how these transfinite recursions are. So there are 6 terms in this union. There's 1, 2, 3, 4, 5, 6. The 6 terms in the union are ordered left to right, of course. And the 2 Cartesian products are given the lexicographic order with standard less than on the ordinals and standard less than on the rationals. Uh, I did say some wrong things. I have to fix a little bit. I did say some wrong things about down here. I think this is not actually dense because I'm skipping some stuff. It's not actually dense, but it turns out it's not important for the argument. Um, you extend it. Once you have a invariant maximal set that's invariant with respect to the stuff that's relevant, you can just extend it to a maximal set that's maximal with respect to everything. Every partial thing has a total extension, so to speak, right? You can always do that. So that was probably not done perfectly down when you won't see the actual formal proof. The formal proofs in my uh, draft has to be fixed a little bit to take care of this because this is not actually dense. There's some skipping around. All right. So less than double star is the linear ordering on W where this comes. So this is the subtle one, the well ordering. Minus one comes first. Yeah, that's not too important. Um, what comes next is this thing way out here. This is right here. This is what comes first, which is really in the second half. I mean, comes second. And then this comes third because this just tops off this. And then this interval, this interval cross 0, 1 comes fourth. Uh, let's see. Yeah, that's right. This comes fifth because this is bigger than this. Sorry. You see, these are this is the set of ordinals less than lambda n plus two, and this is actually lambda n plus two. That's right. So this comes later. So this comes fifth, and then one comes last. And then we extend this in the standard way we did before. This is all extended to using Lexmax. It's extended to k-tuples using Lexmax. Okay, it's not dense. It's almost dense. Yeah, so it's not fully dense. That turned out not to be important. All right, it has left endpoints minus one and right endpoint one, and less than double star is a well ordering with left endpoint 0, 0 and right endpoint lambda n plus m plus one comma 0, and then with the k tuples you just get this. Okay. And now we extend E as we did before. We lift the order invariant set to the transfinite as we did before. And then we make the same transfinite greedy construction based on double star. Of course, we have a new double star. I told you I was reusing less than double star. I was reusing the same letters, but with different meaning. Okay. And then we argue as before that this is a maximal because greedy is much stronger than maximal. And now we have to worry about this. Okay, so this is the interesting point. This is where the idea, novel ideas. Okay, this is not definable. It's too bad. This is not definable. The reason it's not definable is I had to tell you when we're going to go. So we're going. We start in the middle, we go up, then we come back and go up. That's how this transform occurs. But if you do that, you're going to have to tell, this is not very definable because you're going to have to tell me where you quit and where you restarted. Where you quit and where you restarted, it involves two indiscernibles, these indiscernibles. So this greedy set is definable, but it does require these two parameters. But that's all right because we'll use indiscernibility, but we'll only use it for different indiscernibles than these, and that's fine. Indiscernibility allows us to do that. See, we're going to use indiscernibility for lambda 1 through lambda n and lambda n plus 3 through lambda n plus 2. Notice we skipped these two. So if I allow these parameters, I have very good indiscernibility with these, as long as I avoid the parameters. You can do that, you see. By the way, that also indicates a limitation of this method. It's very tricky because you introduce parameters when you do delicate, when you have non-straightforward uh, order of the transfinite recursion, and you introduce parameters, and the parameters sometimes are deadly, but not in this case. It's set up to be all right. Okay. So we have the indiscernibility as before, very similar to before. We have this core that you're in, and we have these things are the only things that we're going to be using because they have to be everything is aimed towards being in the domain of F, right? Okay, so these are order equivalent, but F, remember, is living in the rationals. Yeah. So we assume that Xi uh, is either -1 or 1, or Xi is in the core, or if Yi is in here and or Y is in the core, then Xi equals Yi. All right, that's the hypothesis. Then we get this indiscernibility that X is in here if only if Y is in there. Okay, and that's clear from the indiscernibility of I and the fact that we're only using these two parameters to define this set. We're only using these two parameters. So we can do this because all these indiscernibles are not the same as these. Okay. Now, now we just have um, we just state what we've already proved. We've done that. Now this is a kind of a technical statement, right? So you know that I'm going to follow it through with something more meaningful. And here it is. We're going to prove now that if I have this thing and -1 and 1 is not affected. So I'm going to run to 1104. So I'm going to speed up a little bit. Well, I'm going to speed up a little bit. I have a little too much material here. All right, so when -1 and 1 are not affected, remember, not affected means either you're not in the field at all or you're the identity there. There's several ways to say that. Um, so if I have the situation where neither -1 nor 1 is an endpoint, so I've got a central interval. It may not be -0.5 to half, by the way, but it's a central interval. -1 and 1 are not an endpoint. And it's not affected by F. And -1 and 1 are not affected. That situation, then I claim that I'm really over here. I'm really over here. By over here, I mean up to isomorphism. Okay, so let me do that. Okay, and that's pretty easy to do. First of all, any intermediate interval is the same as -0.5, because this whole book is order theoretic. All right, order theoretic. I mean, order theoretic respecting the fact that endpoints -1 and 1 are not to be ever moved. I mean, excuse me, not to be moved under isomorphism arguments. Sorry. Yeah, I didn't mean. Okay, so this is pretty clear. And now what can I get from this? What can I get from this? This means that G has to be fully usable because we proved that this is fully usable. We just did that. And full usability is preserved under full isomorphism. This is something we did quite a while ago. It was called stability of usability. So immediately from here, we get that if minus one and one are uh, not endpoints and not affected by F, then not endpoints of J, then we automatically get full usability. So that's the point here. And that's a big hunk of just assuming minus one and one is not affected. But what else do we have to worry about? We have to worry about uh, maybe minus one or one is an endpoint. So what about this case? When the inf is minus one. Then we can get an extension which is fully isomorphic to some strictly increasing f. You see, if the inf of j is minus one, uh, then we can do this. Actually, we have to be a little careful. If minus one and one, if the inf of j is minus one and the sup of j is one, then we have a trivial situation that that we taken care of a long time ago. Essentially, we know that it extends to the identity function, still strictly increasing. Okay, so therefore, it's pretty clear that we're down to this case if the if is minus one. And if the sup happens to be one, in other words, the endpoint one, then minus of G has an extension which is fully isomorphic. Now, if you remember in the stability of usability, there was a thing called the minus of a function. And that is G of minus P is minus G of P, which commutes with the additive inverse. Yeah. The minus. Now, G is strictly increasing and minus of G is strictly increasing. All right. So this is just a way of talking about the symmetry between minus one and one, right? Okay. So from this, we immediately get that if J actually does have an endpoint or minus one or one, then we have full usability because we have the old theorem in the stability of usability that fully usability is preserved under full isomorphism, and it's also preserved under taking minus. In other words, G is fully usable if and only if minus of G is fully usable. Okay, so therefore we get that every strictly increasing f, which affects neither of minus one one, is fully usable. All right, and that's a a good solid sufficient condition. Okay, now there's another kind of sufficient condition that does not in any way, shape, or form uh, require that involves the possibility, the strong possibility that minus one and one affected, are both affected. And so far we have zero is not affected in the first necessities we had. All right, I better not do this. Zero, zero wasn't affected, and zero wasn't affected in the one we just did. But now we're going to go to radial. And radial, we can easily have, uh, we normally even have uh, minus one and one being affected because we have f of minus p equals minus f of p. So f of minus one equals minus f of one. That accommodates f of minus one to be something quite different than minus one. Can be any non-negative number, uh, bigger than -1, and f of 1 would be a corresponding positive number smaller than 1, right? So this is quite different, and this also works. And okay. And the way this works, so I don't want to say too much about this because I want to go on, but the way this is done is it's the same technique, but we use a simpler space. Here's the space from minus lambda. Now here we use minus ordinals, ordinals and minus ordinals. Of course, minus ordinals are smaller than all positive ordinals or non-negative ordinals, and the ordering on negative ordinals is just what you expect. Um, Minus omega is certainly going to be smaller than -5. Okay. All right. So the linear ordering is kind of obvious. Well, you got to be a little bit careful because you got this. Yeah. So you um now what did I do? Maybe I made this wrong. Oh yeah, it's this little guy times this smallest one times this union this plus the biggest one. Yeah, but I notice I reversed this because remember we're supposed to be radial. So I'm actually going to W is actually literally radial. Radial in the transfinite sense. There's also radial in the rationals, but there's also radial in the transfinite sense if you have positive and negative ordinals. And so you have to bring in the radial nature of the rationals also. So that's why this is -1, 0, and this is 0, 1. All right. By the way, there is a little thing you have to be careful about. These two parts, in other words, this Cartesian product and the other one, they actually intersect. They have a unique intersection point, which is 0, 0. Just as you expect with radial. Radial means like that. You start at the same place. Okay. Uh, Let me go through. All right. So the ordering is obvious, but this ordering is not obvious. So the idea is this. You have to break a tie. You see? You have to break a tie. And you go, this is the order. You break the tie, you just make the negative ones have precedence. And this is still well ordered. You see, this is well ordered because you're going to use the ordering of the rationals on here. You're going to use less than Q. Where is it? Yeah, where is it? Where is it? Where is it? Ah, here we are. Right. I go like this until it goes out to the end. All right. And then you can show that this actually works, that you get, you do the same thing. And this is the core. The core is these two intervals that we start with. And then we do. Okay. So we get that G is usable. So this is radial. And there's a lot of functions that are subradial. In other words, functions that are nice, that have enough symmetry as to what is going on, uh, purely order theoretic symmetry, that they extend to a radial thing. So the theorem is I should say every radial. Every strictly increasing. Yeah. Okay. And then in here, I actually try to consolidate sufficient conditions the other ways of talking about things, but this is all the red meat. And then here I talk about how ignorant I am and talk about the most basic open questions that I don't know quite how to do with a strategy for possibly attacking them. Now I want to briefly talk about joint usability quickly. Uh, so let's release the requirement that F always be finite. So joint usability means I have a bunch of functions. It means that every order invariant, every constraint has a maximal invariant set that's invariant, simultaneously invariant with respect to all the functions. Simultaneously invariant with respect to all the functions. One fixed maximal set. This is an important generalization for a lot of reasons, some interesting reasons. But the only result I'm going to mention here, and there's a lot of open questions, I think, here. But here I can get a lot of negative results because there's collisions, there are conflicts between the different functions, yes. But here, uh, I define an initial interval extension is G is of the form F union identity on the interval 0p, where F is finite and P is less than or equal, is greater than 0. That's an interval extension. Actually, I could probably even, because it's trivial. Yeah, it's trivial. Uh, well, but I committed myself to interval extension means non-trivial. So let's leave this alone. Uh, uh, actually, I did something bad here. I forgot to say, and G is strictly increasing. Yeah, that's always, assumed. All right. So the theorem is that any finite list of strictly increasing initial interval extensions are jointly fully usable. And this generalizes, stuff that we know how to reverse. So this statement is also, equivalent to con SRP and all that. Yeah. But this is important because I can put conditions now on the nature of those intervals or put conditions down on the structure of these initial. See, there's a notion of a detached one. Detached would mean that F isn't defined, that P isn't sort of affected, that P is not affected by F. That's a detachment. If I have these detached, then I conjecture that it's equivalent to Kahn, the Malo hierarchy. In other words, I know how to prove this stuff from the Malo hierarchy. Uh, Now, I don't do any reversals because I don't want to touch any other reversals, any other serious reversals, in this book. But you can see that now we have a lot of more flexibility in terms of what cardinals I can run up and down. So I am going to say something about, some conjectures about that also on this section on joint usability. All right, so I think that I've gone over a little bit and I'm now done. Thank you.